Dear students, as you know, there are a lot of techniques available for the characterization of nanomaterials. Either it is structural characterization, morphological characterization, or optical characterization. So today I am going to discuss X-ray diffraction technique in brief, which is mainly used for the structural characterization of nanomaterials. Just see the XRD spectra of bulk and nano-sized ZNS. It is clear from the spectra that the peaks of the bulk ZNS are very sharp in nature. You can see the Miller indices of all the three peaks. But if you compare it with the nano-sized ZNS, the peaks in case of nano-sized ZNS are broadened. And why it is so, now I will explain you why the broadening occurs in case of nano-sized ZNS, even though the Miller indices remain the same. So coming to the next slide, you can see the various reasons. Basically there are two reasons. First of all, in case of nanocrystals, the lattice planes are very less in comparison to the bulk material, which normally leads to the broadening of peaks in the diffraction pattern. In the second case, when you synthesize a nanomaterial due to the occurrence of lot of defects like dislocation or twinning, so microstraining of the crystal structure can occur, and it can also lead to the broadening of X-ray XRD peak. Now, what is the basic application of X-ray diffraction? Just see this slide. So, lot of grains are oriented in a random fashion. This is a case of polycrystalline material. But what is the application of XRD? So with the help of XRD, we can find the size of a single grain or a single crystallite, even though there are a lot of grains that are visible in this slide, but we can find the size of a single grain. Now how to find the size of the single grain? Now this formula was given by the Schurrer, and it is called Schurrer formula. Basically it is D is equal to 0.9 lambda divided by beta cos theta. So D is the grain size or the crystallite size, and lambda is the wavelength of the incoming beam or the radiation, and beta is the full width at half maximum, which can be finded out from the XRD spectra. If we go back, you can just see that you can find the full width at half maximum from here, and theta value you can find out from the 2 theta, and just put it in the formula and you can find out the grain size. Now going ahead, I like to give you some examples of the grain size measurement. So this is a case of L16 capped zinc sulfide quantum dots. Either they are doped or undoped. Even the effect of doping can be seen with the XRD, and the effect of capping can also be seen. If you remember, I explained you in the class the role of capping. Why we cap the nanostructures. Basically it is used to control the agglomeration of the nanostructures, and doping is normally done to get the metastable states and to get the photoluminescence in these kind of nanostructures. Now going further, see this is the XRD pattern of the uncapped ZNS, and 0.01% L16 capped ZNS and 2% L16 capped ZNS. So again the peaks are broadened, but the grain size will tell us about the basic difference. You can see that the grain size from the first peak, XRD's first peak, we find it the grain size or the crystallite size from using the Schurrer formula, and you see with the just increase in the concentration of capping agent, the grain size is decreasing. Again it is explaining the quantum size effect, which says that with the decrease in size, the band gap increases or the other parameters change. Now going to the other example, this is an example of doped case. In this case manganese doping is done, and this is a comparison of the three nanostructures. Again we got a broadening in the peaks in comparison to the bulk, and again we find it out the grain size using the Schurrer formula, and you can see that with the change in the parameters of different nanostructures, the grain size varies. So it can give us, it can explain us about the various structural parameters of this kind of nanostructure. That's all.